check over my shoulder. Hopefully it's working. It says recording. Live. The internet can totally see us now. Well, I don't know if they can see me, and it says an error occurred. But, you know, we'll get there. I think I can refresh this and make this work. So, there it goes. It's working. Quick question for you. Am I going too fast? Am I going too slow? Okay. Is this about the right pace? I don't know what's good. And first time I'm teaching this type of class also. And the first time I'm teaching this class, it's a lot of things where I can get this wrong. But I would appreciate any feedback you have. And you could even just anonymously write a note and stick it into my door. That would be fine, right? Right?
Ignore the cover.
That's right. I was going to say, and the fingerprinting. Yeah, sorry. No, I was going to find a way to make a Qualtrics that's, and of course you have to trust it's anonymous. How about I hand out a survey, or I'll hand out paper that you can. I don't know a way you can do it, but type something up, or you can just do it regularly. I promise I will not hold a vendetta. You can say critical things. In fact, you are my best friend if you can be critical about class, because that's how you can help me try to make it better, right? There's nothing I do that can't be made better, and criticism helps get there. Now you can be mean too. It's fine.
I'm going to be honest, I don't see a lot of cookies.
Okay. Should I call on the intercom? We get an order of cookies and maybe a keg. Maybe two? No, sorry. Yes. Okay, that's good. If anything changes, let me know. One thing Dr. Alloway just mentioned that was really important, and I neglected to do so, and I meant to. The parameterization of gamma and inverse gamma changes from text to syntax almost routinely, right? Sometimes people code alphas and betas in one way where they're what I did. Sometimes they might be 1 over, or one of them might be 1 over the other. So what I had done prior to building the syntax was I went and I figured, actually found the PDF of each of the distributions, figured out what the PDF looked like in R, because that's what I'm used to, and then went to the manual for JAGs in their distribution section and looked at their PDF and mapped them to each other. So when you're using inverse gamma or gamma, there's a lot of different forms out there to worry about. Just a heads up. The good news is, what I had found when I did this was that the R parameterization maps onto the JAGs parameterization. So when we call it a rate in R, it's a rate in JAGs as well. So, okay. I meant to say that, but then I dropped it. Okay. Going back to our syntax. Once again, recapping, we named a bunch of variables in R in our data, and then we submitted those to JAGs where we had to name each of the parameters. We used the parameters in creating the conditional distribution by creating a weight, dot hat, and then forming the likelihood from it. One small note on that, if you have a very large model, that will slow JAGs down or cause memory issues, because it's actually going to create in memory a weight dot hat for each person. Whereas if I had just taken all of this syntax right here and put it where you see weight dot hat down here, it wouldn't create it, right? So it potentially has another variable to track when this is happening. Now, I'm going to tell it don't track the variable, because we can tell it which ones to use, but it still can slow things down. I worked with a student who finished her PhD last semester. She was doing a semi-parametric structural equation model, which effectively is a mixture model with, like, one of her conditions, 200 classes. And then, but she doesn't care about the classes. She marginalizes across the classes to go get a different version of the SEM result. But in one of the steps, as we were working through the JAGs code, I said, I wonder if this will make it go faster. We kind of recoded things, and sure enough, I don't know that it went faster, but it certainly didn't crash as much when it went. So it's memory versus processing speed. But anyway, that's just each person in this.
Well, sorry,
theory,
each for a given predictor value.
Yeah, possibly. It depends on the design.
Sure.
So a variance has to have more than several, depending on where you're at, observations underneath it to make it work. Here we could actually have a different, we could take tau and make it equal to some other function. I'm going to do this later on. And one easy place, each of the predictors I could enter in that function, make it a linear model of tau, and in this case it would be, take log of tau to make that work. I'm going to do that a little bit later in class today. But yes, you could easily make it so where you can make extra variance terms and check whether or not that makes sense. So this is where we're going. That's where homework is going to go. Just because I'm trying to I'm trying to take what I learned also and shake the world a little bit for you, which is you make the model, right? And actually in frequentist statistics, you make the model as well too. You control it. So if someone tells you that's the assumption, you say, I changed the assumption. I don't buy your assumption. No, I don't know. You say that, you probably get in trouble, but Templin said, that's better. Templin also said, let's have beer in class. Right. Wine, anybody? Would that be better? Okay, it's fine. We could do that. Mixed drinks would be fine too. That would be fun. But that's a Friday afternoon class. This here, the next step, the error values that you see in that likelihood, I'm creating that because I wanted to go and create a variable to track in the chain as well. But first, let me just show you what I'm doing. After I get through the likelihood here, the next step, I actually created a sigma square variable that I said was equal to 1 over tau e. Because I hate precision and I like error variance. And even the error variance is hard to comprehend because it's units squared. I switched it back to the scale. So really, I'm going to track sigma squared error. And for comparisons with the linear model from frequentist, I actually took the square root of that in the chain as well too. So we have the residual standard deviation, residual error variance, residual variance as well. So you can create other variables like we just did to create weight.hat. Also, you'll note that we discussed this last time, but our parameters, the beta for group 2, the conditional main effect for group 2 and the conditional main effect for group 3, was the difference between group 2 and the reference group when height was 0, or the difference between group 3 and the reference group when height was 0. But we never created a difference between group 2 and group 3, right? This is where I was getting into the multiple comparisons in question at the end of the last lecture. We can do that too. So here I created the mean difference. Now again, this is the conditional mean difference. It's when height equals 0. But I took beta 3 minus beta 2 to create the difference between group 2 and group 3 when height equals 0. So now I've got all three paired comparisons of the conditional main effect possible. The same thing can happen if you are doing a mediation analysis. You want to do a simple slopes, like where you want to go and actually create the value of the simple slope throughout. You can do that as well. You can get all sorts of fun things with this analysis. The question I left you with, or we started with last week, was when you've got, you note here, when we're coding it this way, there's no worry and no thought about multiple comparison problems. Okay? It's not even there. It doesn't even enter in. We're going to have 3 posterior distributions. And from those, we're going to make claims about differences between groups when height is 0, in this case, just to make it simple. So that's a little bit weird, right? Because, I mean, usually in my training, I remember going through a lot of, oh, we've got to worry about this. I think we still have to worry about it. It's just a different worry now. We haven't seen where the worry is yet. So there's nothing we're doing to reweight the model because of it. Any thoughts or questions about that? Anybody suspicious? Who want to raise an eyebrow?
Yeah, so I guess with multiple comparisons, the worry is, which kind of comparison process am I using? How does it adjust my p-values? And here you're going to have posterior distributions to think about, okay, obviously the modes or means are different, but you still have to think about the uncertainty you get from your posterior distributions. And so how much overlap do you want to say, yeah, these are actually different?
Yeah, well, and I think that's it. What you're going to see with us is for each of these parameters, we're going to get a posterior distribution. We're not adjusting the posterior distribution. The way that we built our model is based on our prior belief and our data belief. And the posterior distribution is the posterior distribution. What we can adjust at the end is where we think, if we go and look at the posterior distribution and we figure out which quantile 0 happens to be within it, right? That tolerance for where that quantile is the risk that we would change, right? Because if 0 is at the 95th percentile, the 95th quantile, right? Is that significant? Well, there's not really significant. Significant isn't the word we talk about in Bayesian. Is that are you likely to conclude that 0 is not in your highest posterior density interval? It's a harder thing to think about. But I think it's interesting about that because the emphasis of Bayesians, they really hate the idea of the significance test, right? And yet they go and do things that we would do in a frequentist world. It's a little bit different because the HBD, the theory behind it is a little bit different and so forth, but the result may be the same with saying, well, I don't like the significance test, I like confidence intervals, because that's what it equates to sometimes. But we'll see that coming up in just a moment, okay? The other thing I wanted to note, in the book it talked about creating an R-squared. The R-square in the book I shied away from using, and the reason for that is it was using MLEs from the model to calculate it. And I thought, wait a minute, I can calculate an R-squared at each step of the chain using model parameters. And I thought about how to do that, and I kept coming up with the wrong things, so I Googled it, and of course, Andrew Gelman has a nice way of doing this. I thought it was actually well justified. It's based on what happens in another field of biostat, in survival analysis, and how to calculate R-squared, and it's built so that you don't calculate an R-square over 1. So here's the issue. R-square is always residual variance, or pardon me, variance, what the amount of variance explained. Y's variance minus residual variance over Y's variance, right? If you think about doing that in a Bayesian way, Y's variance, we're not going to put a point estimate in for Y's variance, it's going to have uncertainty. Our residual variance is going to have uncertainty, right? So at every step of the chain, you might have a different Y and a different value of the other variance accounted for. The question would be, at what point do you have a ratio that goes over 1? Right? The way that this is calculated is taking the variance of the predictor over 1 plus over the variance of predictor plus the variance of error. So that gives you an R-squared that's not quite 1. This reference here talks about a couple different other ways of doing this. I can think of another one that might do it. I just didn't go through the math to make it work. And actually, I did this. One of the ones I'm used to using or seeing is the correlation between the squared correlation between predicted value and observation. You've seen that one before. I haven't worked the math out to see how it relates to this, and I haven't worked it out to do everything else. So I'd rather just go with something here. It seemed pretty the paper seemed pretty rational explanation. But that's one of the nice things this gives us, is now we get a range around R-square, which is also cool, right? I think. In this example, it's not as cool because R-squared is so high, but if R-squared were lower, I think you'd see it to be a little bit cooler. Okay, so all of this syntax right here is the JAGS code. Any questions? I ran that. It's now in my R memory. Now, I want to tell JAGS the parameters to follow, to report to me. So now I create a Bayesian full model parameters object in R. And the values that are in this is just what we call an atomic vector, just a series of string variables, character variables. Those are the names of the values I created within JAGS themselves, the names of the JAGS parameters. So each of those 6 JAGS parameters are there. I added also the difference between the group 2 and group 3, which I created. It's not a model parameter, but it's a consequence of model parameters. Likewise, sigma squared, sigma, R squared are also included. And I want to calculate something called the deviance. At every step of the chain, I want to calculate the model likelihood based on the parameters of the chain. That's what effectively the deviance is, log likelihood. But that's what it will be. This will come up in model comparison. If we want to do Bayesian model comparison, the deviance shows up. Questions on this? No questions. Okay, so create the Bayesian full model parameters. Now, the Markov chain draws a series of random numbers. Random numbers are really pseudo-random numbers in R because conditional on the random number seed that you choose, the sequence of numbers will be the same. So to me, it's important to set your random number seed because you may want to reproduce the numbers that you have for reproducibility's purposes. So when you run multiple chains in JAGs, there's a little bit more complication to figure that out. You have to create a bunch of values, of initial values that tell not only this RNG is random number generator, along with the seed to go with it. Copying and pasting all this code will work just fine, but basically each chain has to have its own unique seed value. So I started by creating my seed, which was, I just put the date where I was creating the syntax in. And then for each of the chain values, I updated that with a value of 1 at the end. So they all have a unique value for the random number as they go through. And that is where we have to submit that to R. So I don't know of a good way to tell you this. It was very hard to decipher what this is. But these are the 4 random number generators that are come in base R. I like the super duper. I just use the default Wickman Hill. I don't know the difference between each of these. Someone probably well suited in computational values will tell me which one's better. I don't know which is which. So anyway, you're familiar with random number generation then, I take it, right? The seed and everything. And there's reasons we want reproducible, right? We want to be able to give our code to someone else in our data and have them get the same numbers as a baseline to start. So that's sort of it is. One thing I'll also note in the in JAGs, you can run JAGs in parallel. But Martin Plummer in the creator of JAGs explicitly states in the manual that the random number generation in parallel is, because of the way that seeds work in parallel, it's more complicated, and it's currently not reproducible. But in the future update, it should be better. So just a note with that. So that's part of the reason why we're going to be worried about. That makes me worry a little bit about what's going on when you can't get there. Okay, thoughts, questions? We're finally ready to run JAGs, right? We created our data, we created our parameters, we created our model syntax, we created our random number seeds. Let's run JAGs. So the run JAGs I'm doing is essentially using the rJAGs package, which is the one that Martin Plummer created with JAGs itself. It's more verbose. You have to do more things to make it work compared to the R2 JAGs. But I want to show you these steps just so we know what we're doing. Now, one thing to note, though, is that JAGs has what are called modules that it comes with. And these modules create samplers that work very well under certain circumstances. And the first one to note here is the GLM, the General Linear Model, or Generalized Linear Model module, because when you load that, it will now know what to do with all of your betas that you specified to be univariate, normal, and prior. Basically, it'll say, oh, this is a linear model. I'm going to go and sample beta from a multivariate normal rather than sampling each beta set from a separate univariate normal. That sounds like not a big deal, but there's a really big gain in efficiency because we've selected the conjugate priors, it's going to go and do a Gibbs sampling step with it. And this is the part that threw me for a loop when I started coding this, is I was like, wait a minute, why are you not adapting? Gibbs sampling doesn't need adapting. So you're going to see that real quick. The module DIC, I also load. DIC is the deviance information criterion. That is a model comparison statistic that comes out of the Bayes analysis. But that gives us the deviance value. So when I ask for it to give me a parameter called deviance, it won't do that unless I load the module DIC. So now, first thing to do is to submit my model and all of our stuff to JAGs to compile, which basically means it goes and figures out where we're at. That function is called the JAGs.model function. And typically it compiles and adapts, but here I'm turning off that adaptation because I want to just control that myself. I like doing it because when we get to complicated models, adaptation is efficiency. When we're not doing Gibbs sampling, we may want to specify better versions of adaptation in JAGs because it might shorten the length of the chain considerably. We might be talking about days of our life we're getting back, right? So that's why I'm putting this here. That's my objective. So I do this, and if it worked, what you should see is it's compiling the model graph. So basically it's figuring out what are the nodes of the graph. We have 30 observed stochastic nodes. That's our sample size. It's all the y's, the weight values. Unobserved stochastic nodes is 7, right? We have the 6 betas and the 1 residual variance, in this case tau. So we can figure that out. The total graph size comes from all the parameters and all the values that we created to go along with that. So that includes R squared, that includes weight, the hat variable, that includes the error variable that we used in R squared calculation as well. Questions? Okay. Next. Okay, so now we've built the model. It hasn't run anything for us. I'm going to tell it, hey, adapt my model. What's adapting do? In this case, because, again, next week is algorithms. We're not going to talk about now, but right now this algorithm that it's going to choose doesn't need adaptation. Because we've picked conjugate priors, we can sample directly from the posterior distributions. We don't need the adaptation because there's nothing to adapt, is what I'm trying to say. So here I can hit the adapt button and say, oh yeah, it's been adapted. Sure, you didn't see anything happen. If it was adapting, you'd see a progress bar moving to wherever it needed to be to figure out, in this case, the width of proposal distributions. So samples is where we want to, or now we're ready to run our chain, right? The way that JAGs typically works is adaptation happens before the actual chain itself, and then the chain is a long chain that will include your burn-in period and your post-burn-in sampling. So here, I told it, I want to run 10,000 samples. The other part of this is that the thin equals 1. That means I want you to record every single value that comes out in the chain. I'm not thinning the chain. We'll talk about thinning the chain when we get to Metropolis Hastings. Because when we have an algorithm that's not as efficient as Gibbs, sometimes we're going to reject values that are proposed to jump to, which may induce a higher correlation from one iteration to the next. Generally speaking, you run a long enough chain, you don't need to thin it. You've sampled properly the whole space, but sometimes you want to protect yourself from that, so you thin out steps in between so that your values that come back have very little autocorrelation in one lag between it. Okay, so this is where you'll see a progress bar running. Number of iterations. I picked 10,000. Is that a lot? Is that enough? How many of you think that seems excessive? How many would you want more? I don't know. That's the problem with this. It's really hard to tell ahead of time. I'm going to tell you, in my head, where I picked 10,000, it's actually probably overkill for this model. And the reason for it is we have an efficient chain with Gibbs sampling. We have a model that comes from a really known distribution that has a single peak. And so we're gonna quickly get to the center of the posterior distribution, and we're going to jump around it with pretty much no autocorrelation from step to step, or very little autocorrelation. So we don't need a lot of values. How do you know that ahead of time? It's experience, right? That's it. I could tell you this after 20 years. That's what you need, right? So whenever you're in doubt, pick a big number. So we just ran it. That progress bar ran 4 chains, ran 10,000 steps. That went pretty quick, right? So that's pretty good. And then, so what you end up seeing in the samples here, if I were to show you, is all of those 10,000 values times 4 chains. All of them. That's a lot of data. Let's imagine we picked a burn-in of the first 5,000 steps. The first 5,000, again, arbitrary. We probably want to look at our sample's value and see where we figured out burn-in. Unlike a lot of the statistics out there, picking burn-in is just an arbitrary point, and it's okay to cheat by looking at it, I feel like. You just want to make sure that the tail end is long enough that you have a good sample of it. But here, I'm going to cut off the first 5,000. If we were to look at this, and actually I think I have it. Hang on here. I need to get rid of the big text below. There we go. Here we go. If I were to go and I can actually plot this for you here. Let's plot these samples to look at them. What you're going to see is phenomenal, but this is what happens with a Gibbs sampling algorithm. When you look at these plots, right, maybe iteration 1, that's Gibbs sampling. It literally finds, because the core, we're going to see this next week, the core of the algorithm that works in this case effectively uses least squares as a driver, right? So in iteration 1, you pick random values of variance, and pick random values of whatever. Those may be far off, but after the first iteration, it goes and says, okay, I'm going to go figure out the core, least square estimate, and then adjust based on prior. And that'll get you really close to where the center is. And then after that, it starts to wiggle around. So literally one chain of burn-in would do this. You try to publish a paper that has one chain of burn-in, I'm going to tell you that's not going to go well. This is another reason why this is probably simulated data. But this is really, really quick, right? So those are our entire sample. So let's just go and protect ourselves from reviewer 3 and cut down. Have you seen all the videos about reviewer 3? Go Google YouTube reviewer 3. There's some nice, it's sort of a academic meme that goes around. It's always reviewer 3 that sinks the paper. Anyway. I'll just tell this story. There's a video I used to show. Well, so in this country, recently, there have been a lot of problems, sort of tensions between different, different groups of people and so forth. And one of the groups that seemed to get a little bit of publicity recently that uniformly people say is bad is people who are kind of Nazi-leaning, right? But there was a movie made about Adolf Hitler in German. It's a meme, internet meme, and there's subtitles. And there's one with him about reviewer 3 at the end. So before that whole group thing happened, I would be like, oh, watch this, it's really funny. And now I'm kind of like, yeah, I don't want to go and even talk about that. But there's lots of reviewer 3 videos out there. Google it, just see what you can find. I won't play one right now. It's probably going to be really out of inappropriate for class means. Okay, so let's check convergence. How do we check convergence? First question. We check convergence in multiple ways. The first way is our eyeballs. That sounds really bad. Does it look converged? What am I looking for to see if it's converged? I want to see that this fuzzy cat, it looks like a fuzzy caterpillar. And a puppy. Oh, maybe not a puppy. If you see a puppy, that's not converged. You want caterpillar here. Butterfly? No, that's too late. Here, what we end up having is we want to see this. This is a plot where each iteration's value for each chain is overlaid on top of each other. And you can't see the difference between the chains. You can't see them move out of the way. That's what we want to see. We want to see those posterior distributions run on top of each other. We want to see that they're the fuzzy caterpillar, that comment means that there are literally, you're picking values that are fairly different at each step, right? And what that's doing, when you put all those chains together and you get this posterior distribution, is when you see a bunch of fluctuation at each step, it means that every value is being drawn around this from each step, from each iteration. That's really good. That's what we're trying to see. Now, there's quantitative ways of looking at this as well, and again, you can't plot everything. And when you get into the latent variable models, sure enough, you're going to have factor scores or your latent traits as parameters. Good luck looking through 1,000 sample size of those, right? So it's not going to happen. So what we often do is some other type of convergence diagnostic. The one that is, I would say, by far the most popular, is the Gelman and Rubin diagnostic. You can find out more about this by reading the text. You can also find out lots of texts about it. Gelman and Rubin effectively is a ratio between chain variance to within chain variance. When you think about that, it kind of sounds like analysis of variance. And the Gelman and Rubin is sort of like that. So we want a value of 1. We want the between and within chain variance to be roughly the same. And so Gelman goes and gives us these values. It actually gives us a point estimate of that ratio. It's a scaled ratio, so it's not exactly a ratio. And it gives us an actual confidence interval around it, which is funny. Back to frequentist. And then we just can't give up on each, right? You can't give up the frequentist. But then it also tries to give you a multivariate one, which looks at this across all of the distributions. There are certain rules of thumb. This one, people say less than 1.1 is well converged. Less than 1.2 is roughly mostly converged. For this example, this is a softball. It's Gibbs sampling. It's East data. It's absolutely converged. Right? That's the quantitative evidence that we would want with it as well. The reason why it's important to see convergence is if you don't have convergence, you're not sure that you actually have a good sample of the posterior. If you don't have a good sample of the posterior, what are you going to make inferences about? There's nothing, right? So you need convergence to understand the sample from the posterior to go forward. Thoughts, questions, comments? Okay. Now, the other thing that people often talk about is the autocorrelation in the chain. What is an autocorrelation? Think of it this way. We just had 5,000 values of the post-burn-in chain, right? So we have a data set that has 5,000 entries. If we take one variable that has 5,000 entries and cut off, take that variable and move it down one row and cut off the first observation, we could correlate every value at one iteration with every value at the next iteration, right? That's called a lag 1 autocorrelation. We do the same thing with that. We move it down 5. It's a lag 5, right? So there's an autocorrelation function in R that will do this. Lag 0 is the correlation of the variable itself. I don't even know why they print that. Yeah, okay, cool. Maybe it's just to give the scale. But here, this tells you the correlation of each term with lag 1 up to lag 50. Generally speaking, in a typical algorithm of MCMC, you're going to see things like this with R square or deviance, in that lag 1 is like a 0.15 correlation. Ideally, you want it to be 0. But look at each of the parameters of the model themselves. These aren't bad. Tau is a little bit higher. That's because the scale of tau is actually truncated. We have a really small tau, right? We have a really tight understanding what residual variance is in this example. None of this is bad, and actually there's some debate. Some of my colleagues in the past would say, well, who cares? Run a long enough chain, you get not a good picture of the posterior. And they're right. It's not, once you see that nice posterior sample, it's good. It's if you're wondering if you run a long enough chain, you may need to worry about this. This, by the way, will blow away anything from a Metropolis Hastings. In particular, if you get into a mixture model and you've got some categorical latent variables in it, you're going to see autocorrelations of 0.4 with lag 1 or 0.3 or something like that. It's just really slow because there's not a lot of play chances to jump where you go. So often I don't even look at this, but you should probably talk about it somewhere. Questions? All right, so now we built our model, we ran our model, we checked convergence, we said, yep, it's converged. Now we can talk results. Oh, Bayes, who does Bayes? If I just convinced you that it's a really bad idea, it's exotic right now. The summary command gives us a really quick summary, and I didn't change the scale of these, but basically the scientific notation for each. But it gives us the mean of each of the parameters. We can get the mean, like the mean R square, this is minus 0.1, is 0.967. That's the mean of the posterior distribution. And the standard deviation for each of the parameters shows up as well. The standard deviation of the posterior distribution. And you have versions of the time series standard deviation as well. That sort of factors in parts of the autocorrelation. And then you can also come up with the quantiles for each variable. These, if you were to go and build an interval of this, like if you wanted the 95% interval, between like if you have this, or you take this number as a lower and this number as an upper, that's a credible interval, right? It looks like CI, like confidence interval, but we have to call it credible interval because we're different, right? The other part, though, is these numbers look good. We would typically want to go and look at one other part of the model before we saw these numbers. We saw convergence, and we saw good autocorrelations. The part that doesn't get often talked about in linear models, but shows up in latent variable models, measurement models, and psychometrics all the time. That's great at converge. How well does it fit the data? Right? And so the next part of this is how we check that. That's sort of why I'm using this lecture here to sort of go through each of the steps before we get to really complicated models. Now, this is complicated enough, right? When we start jumping into like inverse Wishart or blah, 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 it takes a lot more effort. So one of the ways that people in Bayes like to check whether their model fits the data is using something called a posterior predictive check. Posterior predictive model check, PPMC or PPC. What they do throughout the chain, or basically we're using iterations from the chain, is they take the parameters of the iterations from the chain and generate a data set with it. And then they check to see, so now let's imagine we do this. Let's imagine we do it 1,000 times. I'm going to take the posterior distribution, right, which has 5,000 values across 4 chains. 20,000 values. I'm going to sample 1,000 of those values with replacements. So I have now 1,000 iterations to grab. From those 1,000 iterations, I take the parameters in the data and in the chain, I generate a new data set with it. Really, I only generate Y. Y is my only outcome here. I can't generate X, I've observed it. So I generate a Y. So now I have 1,000. So how many Ys? I have 30 people. So I have 30 Ys. So I have 1,000 data sets, each with 30 Ys. How do I check that it fits my data? Typically, we do some type of summary statistic, usually frequentist, summary statistic to do that. Sorry, I like to make this point. Hey, Bayes, we're using frequentist. Hey, we're using MLE here. So we're going to take a mean, for instance, right? So let's take the mean of 1,000 simulated Ys. Now we have a distribution of all those means. Let's compare it with where our observed sample mean happens to be. If it fits the data, we should see the sample mean in the middle of that distribution. If it doesn't, the mean will be at the tail. Likewise, we could take sample variance. Take, all sorts of things. We take a skewness if we want. We could make anything a posterior predictive model check. The hard part is knowing what's a really valid one to use. And when we get to psychometrics, this is where a lot of funny business happens. I hate to say that. The model fit world, there are some people there who think they're doing good model fit, but they're using bad statistics for it, right? So, but anyway, let's just do this process, right? So I have 1,000 data sets I need. I went and I created a big, long data frame, or in this case, matrix of all of the posterior. So this Bayesian posterior all is 20,000, all 20,000 of those 4 chains of posteriors. And I grabbed the parameter names for it. I created a brand new model matrix because I'm going to do X transpose beta, or X beta to come up with the predicted values. Came up with my intercept and interaction. So what am I doing here? I'm building a matrix here that has a column of 1s for the intercept. I have height, group 2, and group 3, and then I have the interaction between the two. I'm building that because when I grab the betas from the model, I'm going to put them in a vector. I'm going to take this matrix times that vector, and then I get the predicted value for 30 people. Right? So it's a quick way of coming up with a predicted value. figure out the parameter names. What I'm doing with parameter names is so I can put it in order based on the beta, vector, and the model. If I transpose where the parameters are, our JAGs will put them in alphabetical order. That means I'm going to be multiplying x times the wrong beta, and I don't want that to happen. I randomly create, this sample function just creates it's like a sampling with replacement deal. So I say I have up here 20,000 rows. So I take a number 1 through 20,000 where I'm sampling which row number to have. I take it 1,000 times with replacement. So this tells me which iterations to use in my posterior sample. And then I wrote this with a loop, right? So this is a very inefficient code. You could write it faster with apply. I hate teaching with apply. I hate teaching with that stuff. It doesn't work with the way I think about things. So it's just a sequential loop. So here, I'm going to create a vector for the distribution summary, or create an empty data frame for it. Here I'm just taking the mean and variance of y for each. And then I actually do that. Here I'm going to take one observation. I grab the parameters. These are the parameters from that posterior distribution, that iteration. I can create a mean vector using a matrix of these parameters. There's my matrix product. And then I can draw using R norm y. That's drawing from the model itself, right? So this is now my PPCY are my values of drawn y's for all the people in my sample, right? And then I summarize it. I take the mean and I take the variance. I just do that over and over again. And so now, when I do that, I got a bunch of summaries. In fact, I have 1,000 values of mean and variance. Let's create a histogram and compare that to where the observed values happen to be. Frequentist values happen to be. So here's a histogram of the sample mean. That's y. That looks pretty good, right? Oh, that's right. I have to run this whole step to get that to draw lines on it. There we go. That red line is where the observed sample mean is. It's right in the middle. It's pretty good. Actually, that is variance. It's also pretty good, right? The mean is this graph. That's really good. So why you don't often see posterior predictive model checks in linear regression is also why you all don't often see a lot of fit statistics in linear regression. You go to a mixed model or you go to a multivariate regression, now you're worried about lots of things. Because now it's a multivariate normal, and in a multivariate normal, if you don't get your covariance matrix right, there's more observations. But with one observation, there's hardly any way to go wrong. So, thoughts, questions, comments? It'd be interesting to see if we dropped a variable, how far off this would go, but I didn't. I think this lecture's already long enough, right? So, okay, so this actually should have happened before we went and looked at the summary, but I put it in here afterwards because I was like, oh yeah, by the way, we're going to be doing this. What are the model fit statistics that you see in some of your measurement models? Just to get you thinking ahead. Like a CFA model, where would you look for model fit? RMSEA, right? RMSEA is the difference between sort of a comparison of essentially how far off you are by degree of freedom from what's supposed to be the chi-square. It comes from looking at the saturated model, right? The model with just the covariant, every parameter in compared to your model. We could come up with a version of RMSEA also and do that. Alternatively, one of the things that we often see, RMSEA tends to be high. When it's high, what we often do is inspect what we call residuals or normalized residuals. What am I talking about? Take your covariance matrix in your data, the MLE of it, specify that, and compare it with what your model implied covariance, take the difference. That's a raw residual. We can do the same thing here. So now all of a sudden we've got a distribution of what our model is saying the raw residual should be versus what our data are. And that's how we're going to start checking models. But also with RMSEA, you can actually do that as well. You can calculate that at each step in the chain and take a distribution of it too. So lots of stuff that we're going to be able to do. It's almost overwhelming. The posterior predictive model check takes an already overwhelming task, which is model fit, and makes it like overwhelming to an nth power. It's just really, really, really. You can do it in so many different ways, right? We could have it with, here I did mean and variance. I could have looked at maximum value of y. I could have looked at skewness or kurtosis or any of those values and seen what the model was doing versus what happened. Now, I will say that some of these are pretty obvious. If I were to look at the skewness of y, my model, whenever I generate data, it's all coming from normal, although it's actually multiple groups, conditional normal. I'd get a skewness, but it would probably tend to be fairly constant. And that would be because it depends on x more than it depends on the parameters. So anyway, that's the hard part, right? You really have to know your model and know what it's saying about data to really understand why things may work or not work for choices. So in some respects, that makes Bayesian complicated and frustrating. In many respects, as a student, it makes it amazing to learn because now it's going to solidify everything you learned in every other class. Right? It's now you have to know what the model's doing if they even make it work. And then once you're doing that, you need to be able to check to see how it does otherwise. All right, so we have results. We talked about that. Actually, here I rounded the results. There's our values. We can compare these with the frequentist, shall we? So here's our linear model. We would interpret these pretty much the same way we'd interpret the linear model ones. Here, the first place I want to start with is residual standard error, 7.949. And for us, that would be the equivalent of sigma squared error. Now, there's something interesting about the numbers here. We are not actually comparing the same value. Think about real quickly, what is this value? When we call it an MLE, what part of a distribution are we referring to? Let's call that an MLE. Are we talking about a mean of a distribution? The M, the maximum, is a mode. So we're looking at a mode of variance here. We're looking at a mean of variance here. Okay. In a symmetric distribution, the mean and the mode align. Let's take a look at our posterior distribution of variance, shall we? Do I still have it plotted? Well, there it is, sigma E. This is not a symmetric distribution. It's sort of symmetric, but it's not entirely, right? Certainly not for the variance. So, I remember this basic stat. What happens to the mean in a positively skewed distribution? It gets pulled away from the mode. The mode is what we get with the frequentist result. The mean is what we get when we look at the mean or the EAP from our output. Sometimes you'll see a median. Why I'm saying that is I think that's a commonly misunderstood term by really smart people. I was at a conference at SMEP, Society of Multivariate Experimental Psychology. I remember this is one of these closed societies. It's kind of weird. And then I go, I'm still going to go, right? But we're having conversations with people like, well, everybody knows there's a negative bias on the variance in Bayesian. It's like, well, no, actually, is it negative bias or is it you're comparing a mean and a mode of a skewed distribution? I think that's what it's boiling down to. There's a lot of that goes on. Now, I had tried to calculate the mode, and I think if you look at the HTML file that's on the website for it, let me see if I can do this in a way that would allow me to make this work. I don't know that I will, but let's see. I can calculate the mode. The mode here for our distribution for sigma is actually 12.42. It's still more positive than the MLE happens to be, which was 7.949. So in this regard, there is something going on with this here, with these data, and that might be the influence of the prior that I chose.
Also, since we had only 30 people, right? You chose a super wide prior.
Yes.
So that's not too surprising, I guess.
No, I don't think it. I'm not going to be concerned about it personally. The other thing you'll note, let's look at the fixed effects of the betas. In Bayesian, we had 170.771 for the intercept with a standard deviation of 48, roughly. 170.16 was the intercept in the least squares MLE version. Now you'll note the beta distribution, the posterior is normal. So when we compare the mean and the mode, we're actually probably going to be right on top of each other with it. So that comparison is a little bit more valid, although it's still not guaranteed the posterior will be normal. It depends on how long we ran our chain and what our priors are. But in this case, we know it's going to be normal, right? But in that regard here, we have 170.771. We have roughly the same estimate, slightly higher. The standard error is a lot higher, though, right? Standard deviation of 48 versus a standard error of 29. Right? Those are roughly equatable. Standard error is like, well, the standard deviation is like your standard error of your parameter, right? Your posterior sum rate. And similar to that, the standard error should be that. And if you look at the standard errors of each of the parameters, they are also bigger in the Bayesian standard deviations. Why is that? So here's the interesting thing about it in linear models. Linear models effectively profile out sigma squared. And given the sigma squared, we can calculate point estimates of the betas with the normal, what's called the normal equations, right? X transpose X inverse X transpose Y. And then you've got another feature of that where the standard errors comes from your profiled variance, sigma squared, times X transpose X inverse, right? That's awesome. It's also at a fixed value. And here's the big difference between Bayes and linear models and Bayes not in linear model, or just regular linear models with least squared, is that we're saying, no, variance, I'm not fixing it at a value. I'm letting it go across its sampling distribution. Right? So if I have a small sample, it's going to have potentially a big distribution. Plus, it's going to be the posterior distribution, subject to choice of prior. Right? So what I've done is effectively said, I'm going to actually expect to have a larger range of my fixed effects. Because if you think about what we did, for every sigma squared we did, we could actually trick our algorithm out. So we could fix it so that we could just let it sample sigma squared, and then we can go and get beta from every step of the chain, because that's a quick matrix product. We could do the least squares beta. Even if we did that, we'd see that the standard deviation would be much wider, and that's because we're letting sigma squared roam more. Right? Where it won't matter is if this sample size was like 300, or where effectively infinity happens to lie, because we'll see a convergence. The concept that I'm talking about here is what we call asymptotic convergence. Right? How quickly that variance covariance matrix of our parameters assumes effectively that as n goes to infinity, that's the distribution of the parameters converge to normal with this covariance matrix. We're sort of arguing where infinity lies. Furthermore, if we had lots and lots of data, we'd see the posterior distribution of our variance would look more and more normal. In fact, next week I plan to do that. I have the Gibbs sampler. We're going to just replicate data and show big versus little. So that's kind of the key difference I see in linear models versus what we see in Bayes. Now think about that with respect to measurement models. And this is sort of the first day of the class I was talking about. There are a couple places where we have that same feature show up. And I don't exactly know, this is part of my own personal life course trying to study things, I don't exactly know the ramifications of this, but we've been told a lot of times in psychometric models, these are large sample techniques. And we talked about, the first day I did a Metropolis Hastings, where I said, let's imagine we had calibrated model parameters, and we go and pick an ability versus sample model parameters. We saw the ability distribution got wider when we allowed that to happen. There are certain parameters to our model where uncertainty will be amplified because of the sample sizes we may have. How big of a sample size do we need to have a steady distribution for our covariance matrix? Anyone ever talk about that? It's hard to know. I think it's a lot bigger than what I'm used to using on data, or other people's data, I should say. So we'll find out, though. That'll be something to think in the back of your mind as we go forward. We're getting there, though.
It's interesting, too, how I think about these things and do them. This could be very much just my inexperience these days, but when I look at the frequentist approach, I really care about that standard error, because I'm like, oh, that's a big value. It's going to play to my p-value. When I think about Bayes, like, I kind of look at the distribution. I'm like, okay, that's cool. That's my distribution.
Right.
I
Yeah.
don't care as much about the larger standard deviation of the posterior.
Well, let's take a look at the ramification of it. When that larger standard deviation, I'm going to go look at let's go try to make some inference off our Bayes parameters. We can use the high density, or the highest posterior density, the HPD interval, which again is it's the 95% credible interval that has the smallest range. And most of this will be right on top of what the 95% credible interval is, because they're symmetric distributions for the most part. But now, the bigger the posterior standard deviation, though, the bigger the interval. The bigger the interval, now the inference matters, because this right here are the sort of bounds of where you're 95% sure that parameter should be in its posterior distribution. Now, if we're going to make inference on this, that's where it's going to count, right? It's a lot harder to find. Now, each of our parameters, with the exception of the main effective heights, the results are roughly the same. We want to see effectively if zero's in here. But now we've got multiple comparisons to think about. So maybe not 95. Maybe we should have done 98 or 99, or done a Bonferroni to figure out where that tolerance would be to see if we have one error or however many errors overall. Often we don't even think that way. I don't know that it matters as much, but maybe it does. Probably. Actually, it absolutely matters. The same math that goes with why we had to worry about it before still matters here. The question is, where do you want to adjust your tolerance? But if we did the 95% interval, what we're effectively saying is zero in our interval? Because if zero is in our interval, we are saying that, yeah, it's possible this parameter is zero within this range. Each of the parameters that we have gives us the same. If we essentially say zero in the interval is our non-significant result, which is, again, putting in quotes, not really significance. It's just we could sort of think it in analog. We would not change any conclusion here. But that's because this data set was ridiculous, right? Look at our R-square range, right? It is 97 to 95, right? The 30 people. That's ridiculous. But then your point is well taken, though, because the same thing is going to matter. The bigger that range, yeah, the bigger your conclusion might be different. So power, what's power? How does that work? Gosh, it's a tough question. But it's still something to think about. So what really matters, what you can tell, is the choice of prior actually will affect a lot of this quite significantly with 30 people. Anyway, is this helping kind of get your head around Bayes a little bit different? Questions, thoughts? Uh-oh.
Would it make more sense to think about precision and power in this context?
Yeah, I think you have to think about that, like the width of that interval, right?
Yeah.
Mm-hmm. Yeah, I think that's effectively how wide. Yeah, but then, and this, I'm not as familiar with it. I worked with a person previous to Kansas he was much more familiar, and he was trying to he was putting in grants with power, what he was calling Bayesian power, and had a good number of citations. I never looked at them. So there are people who think of it that way, and I'm just not as well versed with it. But I think it's along those lines. But they also have to think about where the point estimate is. So you may have width of interval versus where you're at, and then what the prior happens to be as well too. So, okay. Questions? Coming down to crunch time here. We might actually make it through. I actually went and tried to fix the residual variance at its value from the MLE. And I reran the code. Now, I reran the code in R to JAGs because this did take a long time to prepare. I'm like, I need to hurry this up. What spooked me, by the way, about when I did R to JAGs before is I was not seeing the adaptation, and I shouldn't. That's okay. It knows what it's doing, but it's fine. Artijax also automatically loads the GLM module and the deviance module as well, so you sort of get protected on that too. So what I had done different was I had just taken the sample variance. In this case, this was the sample, not the sample variance, but it was the value of the residual variance from the sample. Put that in, change the parameters, I changed the starting seed, and then I ran the analysis, and there you see it ran. And then we can take a look at the output. And now what you end up seeing, though, that standard deviation is a lot closer to what we thought with the MLE. Right? It's 29.364, and the MLE is 29.278. Right? Had I run this chain 100,000 times, I may have gotten right about where it happens to be. So the point I'm trying to make is, if I go and fix the variance of what the MLE happens to be, this is sort of a check on how informative my priors are, right? Because I should be getting, if I have a really uninformative prior, my beta should look like the MLE as well, and they are starting to, or they're pretty close to, right? So sigma squared, allowing it to vary is sort of the part that really, like what's key in my mind. Okay, a couple things that we'll probably have to come back to next week, but I'm going to tell you right now anyway. We can do a model comparison. How do you compare models in Bayes? That's a hard part. In regression, R-squared change, is that what you learned? Right? We didn't fit two models. And R-squared change, well, R-squared's got a distribution. Which one? Which part of it, right? I guess we could come up with a change of the distribution. We could do that. Typically, in ML and in frequentist, there's three types of like hypothesis tests. There's probably more than that. The three I'm most familiar with, they're asymptotically equivalent, right? There's the likelihood ratio test, where you fit a null model that has fewer parameters, you fit an alternative model that has more, and you're able to do likelihood ratio. And I believe R-squared change maps onto that because you have to fit two models. I don't know that it's one-to-one with it, but it maps onto it. It's an analog. There's walled test, which is where you fit the alternative model, and you can go and see if you want to, each parameter has now a p-value effectively. Or you can come up with multivariate p-value from multiple sets to see. And then there's, the last one? I heard start here. Score test, yeah, that's right, yeah. Modification index, we talked about it in SEM. Thank you. Score test. And so all three are asymptotically equivalent, which means in N, they should give you the same decision. In Bayes, often what we see is the walled test version, right? Which means we fit the alternative, fit the model with more parameters, and we start looking at the parameters to see if we need to remove those. Occasionally, though, we may have model comparisons where we have wide differences between parameters, or like in CFA, we might want to fit the saturated model simultaneous to fitting our CFA model, and go and compare the two using some other statistics. And that's where we calculate something called the DIC. I wanted to compare, now the DIC, I'll go into this more as we go on through class. Just think of it as an information criteria statistic like AIC or BIC, meaning each model has one. And what we're trying to find is when we compare models, the model that has the lowest value typically is the one we prefer. It weights sort of information in the model versus parameterization, the complication of the parameterization. Right, so you get you have like something to do with the data. This is the deviance, the log likelihood effectively at each step of the chain. And then you add in how many parameters the model has. In Bayes land, we can actually compare this. We can compare models with different priors with it. All right? If you don't like my priors? Fine, pick some new ones. Try it differently. So I'm going to do something different with variance. I'm going to take the log, and in this case, remember, JAGS does 1 over the variance. I'm going to take the log of that and model it. This is sort of a log linear model, although we typically think log linear is categorical data. This is another way to describe. Because if I log 1 over the variance, 1 over the variance has a range of 0 through positive infinity. The log of that now uses the range of the real number line. Because the log of any number less than 0 goes from 0 to infinity. And anything, I'm sorry, less than 1. Log of 1 is 0. Log of anything bigger than 1 is positive. Right? So I take the log of the variance, and I'm just going to create gamma 0. That's what I'm going to say is the intercept of variance. I'm going to put a normal prior on gamma 0. Right? When I do that, I effectively have, did I put a normal? I may have put a uniform here. EXP of gamma 0, gamma, yeah, I'm going to put normal. I effectively create a log normal prior on the 1 over the variance, where I put it, which is kind of a weird prior. It works fine. It still has the same range of variance. Okay, so now I've got 2 models. Why do I do this? So I've been talking about this. What if you have different variances for group? Here's how you can model it. You take log of the variance, and you predict that with your group variables. Now all of a sudden, this is, if we had a gamma multiplying group 2 and a gamma multiplying group 3, we now have reference group variance, or log variance. This is log inverse variance. And then each of the differences between the two. Right? So now we have a model that does not assume homoscedasticity across groups. It's important for homework. But speaking of homework, I got to stop there. That's the cliffhanger. Let me talk about homework real quick. Because you can actually start on homework now, and then by the end of next week we'll have more, and homework is due 2 weeks from now. So let me just go to the GitHub page. I tried to make homework a little bit more challenging, but hopefully in a good way. And if it's, no, I can't go to the GitHub page. Oh, template. Lectures. Nope. Homework. Bless you. There we go. There we go. Homework number 2. First step. I want you to find, bless you again, a model, an article, a journal article, peer-reviewed journal article, where they do Bayes and linear regression, and not in one of the methods journals, not as a throwaway example. Like what I would call an empirical journal, some people would call substantive, which I hate, because I think substantive sort of translates roughly to meaning it has substance to it, and methods does too. So that's how I view it. Empirical research, basic research, of course, if I called it, yeah, methods are basic. I probably wouldn't say that either. So I want you to do that. Give me the article PDF, something you can find online. I want you to be a journal reviewer for it. Write a 300 to 500 page review of the methods only. You don't have to tell me, like, if it's about, like, you know, flower growing or something like that. I'm not going to help. But of Bayes, what were their priors? What were the models? They use any model comparison. Why I'm doing this is I want you to see how people are publishing with respect to articles. And I want you also to write, because you're going to have to write at some point in your life, and that's important. The second is a Bayesian data analysis with write-up. There's a story. Lisa Hoffman will tell you more about the story if you ask her. We did a study, simulated, that had studying the effect of performance in miniature golf. Does anybody play miniature golf? Putt-putt? I don't know if we have anything around here. I have several research questions. There are several variables. I'm asking you to, number 1, take the data and create a very specific sample for your own ID, so each of you has a different data set. Run the Bayesian linear model. One model, you can do one model to answer all questions, just one, and then write up a results section effectively that describes what you did. These two you could effectively get started on right now. The last one is I want you to do a little bit of math to derive the posterior distribution of beta and sigma squares under the Jeffreys prior. That actually you will be able to do much better after we talk next week, because I'm going to derive what is a Jeffreys prior, first of all, I'll tell you that. The second, I'm going to do it with the conjugate prior, which is a lot more complicated. A Jeffreys prior makes a uniform distribution on beta across the real number line, and it has a uniform distribution for sigma squared too. So if I can do it right, if I can teach you right, it's a matter of knocking things out of the form that I gave you before. But I want to do this exercise because I want to see want you to see a little bit about how we go and figure out posterior distributions. But there's a catch. Remember, I can challenge you because you can fix your homework, right? So I want you to try, and if it doesn't work out well, make sure you make an actual attempt at each item. And if you somehow screw something up, I'll mark it up, you can fix it, submit it again, and get points for it. So I'm hoping to use that as my lease to challenge you a little bit more. All right? See you later. Have a great weekend. Thank you. By the way, homework's due in 2 weeks, so.